We are Group 33, and our project is the motion detecting Sentry turret. Our group consists of one electrical engineer, Caitlin Martin, and three computer engineers, Laderma Gary, Michael McAllister, and myself, Quentin Jimenez. Given the overlap of our majors, we have divided ourselves into two teams which are responsible for conquering different aspects of the project while remaining informed on all areas. Laderma and Caitlin will maintain a focus on hardware-related matters while Michael and Quentin target software. The primary goals of this project are to autonomously identify and track targets within range of the Sentry turret, to mark targets by accurately firing paint-filled projectiles at the targets, and to create an enjoyable experience for any group utilizing this product recreationally. To accomplish the goal of autonomously identifying targets within range, the motion detecting Sentry turret will employ computer vision algorithms. The software will then track the targets by performing a series of calculations that return the appropriate position to aim the Sentry turret toward. The turret's stepper motors will then rotate the necessary amount of steps to aim the projectile launcher before firing at each target. The motivation behind our project is multifaceted. Our group wanted to create a piece of technology which could be applied for recreational uses, such as paintball tournaments, as well as security and military purposes, such as the protection of properties and controlled lands. The motion detecting Sentry turret project will be safe for usage and testing by students. However, the technology is expected to be modifiable to suit more dangerous conditions. The specifications for the motion detecting Sentry turret are included in this table. The three primary specifications are an accuracy to a minimum of 70%, a traversal range of 180 degrees horizontally and 45 degrees vertically, and a range of effect between 10 and 75 feet from the device. Other specifications include a power supply duration of 3 hours while the device is running, an ammunition capacity of at least 20 rounds, a weight of at most 40 pounds.
We currently have the chassis containing the vertical stepper motor and accompanying gears that have been bolted together. Here will be where the stepper motor and associated gear reduction that will be for the horizontal component of the system will be connected to. That will eventually be connected to a steel plate with 3 legs welded to it to make up the base of our structure.
Our current computer vision algorithm is effective out to 35 feet, and is most effective between 10 to 25 feet. Past 35 feet, the algorithm seems incapable of detecting any targets. Past 25 feet, detection becomes spotty and cuts out often, with the turret only able to reliably detect stationary targets. Targets moving horizontally quickly are difficult to detect, even within effective range. When unable to see every part of a human, the algorithm may detect only a limb or nothing at all. The camera's angle is an important aspect of the field of view. For optimal results, the camera must be perfectly aligned with the horizontal axis. Otherwise, targets at close range have the risk of cutting off the legs or the head, which makes detection much more difficult.
Here we see a demo of what happens when the turret detects a person. The light will turn on for 5 seconds, then the servo shown at the top right will turn on and hit the trigger mechanism to fire.
We were able to collaborate and achieve successful teamwork even without every group member present through electronic communication, particularly the programs Discord and GitHub. Discord allowed us to set up voice meetings to discuss and plan with each other remotely. It also allowed for direct messages between members, so that if anyone was absent from a face-to-face meeting, they could still contribute through text messages. Our group met at least once every week, and at each meeting, we would affirm how each group member is to contribute to the project outside of these face-to-face meetings. GitHub's main purpose is to let each member of the group contribute to the project's software independently. GitHub allows you to remotely change the code, as well as see and download the changes fellow group members have also made.
A challenge that my group faced was staying on task. The way we overcame it was by weekly meetings, making structured decisions, dividing the workflow, and having everyone reaffirm what their goals were on the project.
In addition to my own desire to see my degree through to its completion, the expectations of my friends and family were powerful motivating factors which helped me stay focused throughout the project.
While we didn't start this project with any particular client, over the course of the building process we were introduced to many paintball players, all of which were very enthused over the potential final project and the final output. We were able to hear of all their different turrets and how having one work using computer vision would be very interesting in gameplay. The main feedback we got was having a design that would be able to handle most outdoor conditions, which could be easily done by weatherproofing the electronics.
The most important lesson I learned throughout the project process, which I will be able to apply to my future work in the industry, was to ensure that the available hardware is sufficiently capable and in sufficient supply to test and retest the software.
The motivation to focus on my group's project topic was the excitement we had towards brainstorming. It was a unanimous decision to make a project that involved an active game and improving it with automation. With COVID-19 restrictions slowly being lifted, we wanted a project to provide entertainment for people who were previously indoors. This concludes Group 33's showcase video. We hope you enjoyed and thank you for listening.